Let's find sector area. In a similar fashion to how we found arc length, we're also going to use the idea of proportions. Think about what you know and what you want to put in the proportion. Something that we can compare, for sure, is again that angle measure. We know that if we want to find the sector area, the piece of the circle shaded right here in purple, then we know that it's formed by this angle, in this case of 100 degrees. We can compare the angle measure of the part of the circle versus the angle measure of an entire circle. That's something we can compare. So I'm going to go ahead and set up my proportion where I know I'm going to compare angle. And what can we compare with the angle? Well, based on what we did, based on what we're trying to find here, we're trying to find the area. So if you think about how you want to find the area, we can find the area of the part of the circle and compare that with the area of a full circle. So we're going to make that second comparison with the area of a circle. And remember that a proportion is set up as comparing the part versus the whole. So let's think about how our proportion is set up. In terms of the angle measure, the part of the angle that I know that I want to find is made up of the 100 degrees. Now, the whole of the circle, we know a full circle is made of a total of 360 degrees. Compare that with the area. Now the area, the sector area, that's actually what we want to find. So I don't know what this shaded purple region is. So I'm going to go ahead and call that A for area. And what is the whole of a circle? We want to find the area of a full circle. The area of a full circle we know is represented by pi r squared. And based on the information provided, we can fill in some more information, knowing that the radius is a value of 9. So plugging that in, one other thing I want to mention here, in terms of units, you'll notice that there is an apostrophe there. Remember what we said before. I know it was very recently how we said that if you think about an apostrophe, you tend to think of that as, in this case, you tend to think of that as minutes. However, if you actually look at the appropriate form of this, it's actually given in terms of a length of measurement, right? So it's actually not minutes. Keep in mind that the minutes only occurs if you actually see it like, let me rewrite this. If you actually see it like this. This is 100 degrees 1 minute because 1 minute is represented as a partial degree. Okay, but in this case, you'll notice that the 9 has an apostrophe next to it. Well, if you're talking about an actual length of a measurement, this is actually in terms of feet. So we're actually talking about 9 feet here. Okay, so just want you to be clear on that. So if I'm going to emphasize that, I'll say 9 feet squared like that. Okay, equals 100 degrees over 360 degrees. And you can see here, all we're left to do is then solve for A. So we can multiply both sides by, this is 81 feet squared pi, right, times 100 over 360, right? And by multiplying all this out, there's a little cancellation here, 81, maybe I should have simplified this out a little bit, right? We're going to see that we get 90 over 4, or that's the same as 45 over 2. Don't forget that there's a pi there, pi, and then this is in terms of feet squared. Okay, so that's going to be our total sector area of this region right there in purple. Okay, all right. Number 4, I'll leave to you. Again, you can just practice your ideas of proportions here. Where did it go? This looks kind of weird here. I believe there should be a 6 there, but you can go ahead and work on number 4. Go ahead and pause the video, work on that example, and then when you come back, unpause, and let's look at in general, what the formula is of sector area. Okay, just like we did with arc length, you'll see that we actually have 2 formulas that we can actually create. Because if you did the previous 2 examples, you'll see that one measurement is given in degree format, and the other measurement, sorry, technical glitches here, circle pop up, there you go. One is given in degree format, and the other is given in radian format. So just like we did with arc length, we need to consider how sector area can be broken up into 2 different formulas as well. One for degrees, and then also one for radians. Okay, so let's go ahead and create both of those formulas. Again, the idea is create proportions. Proportions, proportions, proportions. And the proportions are set up by finding the area versus the angle measurement. And so if you think about a part of the area, the sector area, over the whole area of a circle, pi r squared, is equal to a part of the angle, which we call theta. Compare that with a full circle's angle, which we know in angles in degrees is 360 degrees. Solving for sector area, we see that we get theta over 360 times pi r squared. Okay, if you think about this, what this means here, theta over 360, it's really kind of like saying, like, this is the part of the, and then what this is the area of a full circle. So you're kind of saying, what is the multiplying the part of the area of the full circle, right? Okay, so let's go on to finding the formula for sector area in terms of radians. Again, we set up the same kind of proportion where you can compare area versus angle. The area, sector area, called A, over a full circle's area, which is again still pi r squared. Compare that with a circle's angle measurement in radians, which we don't know. Let's call that theta. That's the part of the angle, over the entire circle's angle, and in radian format, that's going to be a value of 2 pi. Okay. Then, solving for A, we get theta over 2 pi times pi r squared. You'll notice that the pi's can cancel out, and so area is equal to theta times r squared all over 2, just like that. Okay, so that's the formula for sector area. All right, let's do another problem here. A sector of a circle has perimeter of 12 centimeters and area of 8 centimeters squared. Find all possible radii. So what are we dealing with here? Well, in a circle, we know that a sector of a circle, so a piece of this is what we want right here, right? This piece right here. It has perimeter 12. Well, how do you create a perimeter? It means adding the entire outside, right? If you wrap it around, it means adding the entire length around. You can see what we're kind of creating here. How the perimeter of the circle is made up of, what is that? Well, this is an r value, a radius. This is another radius. And, oh, well, that's actually our arc length, right? So the perimeter is equal to r plus r, or 2r plus L. Okay. Oh, wait, I think we had a formula for L, didn't we? Going back to our previous page, we said that arc length can be written as r times theta. We can use any one of these formulas, but I'm just going to go ahead and stick with radian measures just because when we work with circles, we tend to go to the default of using radian measurements. Okay, so I'm going to go ahead and reclassify my perimeter equation as perimeter is equal to 2r plus, and then we know that L is really the same thing as r theta. Oh, and then I guess we also have this extra piece of information that the perimeter is 12. So 12 equals 2r plus r theta. Okay, now in its current state, we really can't do much with this because, well, we have kind of like two variables here, right? So we need to figure out what we can do with this. We have to leave this alone for now. Let's now go to the area of our sector, and that area is 8 centimeters squared. Just as we did in the for arc length, let's look at the sector area. Remember how we created two formulas. If you're a formula type of person, remember you can just memorize these formulas. If not, you can always go with the proportion idea and solve for what you're missing. But in either case, remember if we're working with radians, you'll end up eventually getting to the idea that area is equal to half theta r squared. And so if we know that the area given to us is 8 centimeters squared, 8 is equal to half theta r squared, or I guess another way of phrasing it is 16 is equal to theta r squared. And so the idea here is thinking about how can you make these two equations work out with each other. And hopefully what you're coming across here in your head, you're thinking, oh, this is a system of equations. So how can I solve this system of equations? What's going to be the easiest thing to do? Most likely, I don't think you want to be working with that r value. Instead, maybe think about how you can isolate that theta. So if you divide both sides by r squared, then you can get theta is equal to 16 over r squared. Okay. Once you do that with substitution, plugging your theta back in, right? We're going to end up getting 12 is equal to 2r plus r times 16 over r squared. A little simplification gets us 16 over r there. But in order to work with this, as we've seen in previous units, we can multiply everything by r, and in doing so, we will not have this rational number anymore. So we'll get 2r squared plus 16 if we multiply everything by r. And now it just basically turns into a quadratic. If you solve 2r squared minus 12r plus 16, this is then factorable, right? You can factor out the 2, minus 6r plus 8. And then taking a look at that, you can divide both sides by 2 as well. Doesn't really matter. But 0 is equal to, what will that give us? R minus 2 and R minus 4. Oops, I think I'm running out of room there. So that means that R is going to be a value of 2 and R is going to be a value of 4. So we see that it's going to be possible radii are 2 centimeters and 4 centimeters. Don't forget your units. All right, and last question. Number 6. At its closest, Mars is about 5.6 times 10 to the 7th kilometers from Earth, and its apparent size is about 0.007 degrees. What is the approximate diameter of Mars? Okay, so as you think about what this means, imagine, if we're talking about the solar system here, that from a far off distance, here we are on Earth, and Mars is, let's say, over here, okay? And what we're dealing with here is that Mars is about 5.6 times 10 to the 7 kilometers away, okay? Now, its apparent size is 0.007 degrees. What does that mean? Well, if you're sitting on Earth and you look at Mars, what this is referring to, I'm going to try to give you a very close-up view of what this represents right here, okay? If we're sitting here on Earth, and I'm going to try and draw a face here, right? Here's your eyes. And when you look at Mars, so when you look at Mars, oops, that's a bad line there. When you look at Mars, then what you end up seeing is that Mars takes on this general shape, right? It's a circular shape. And you can basically see how from the bottom to top, you're almost in a way seeing how you kind of create an angle measurement with your eyes of Mars. And so if this is Mars here, with that angle measurement, you can kind of see how you can actually create almost like a pretty close diameter of Mars. That diameter, if you really think about it, it's actually kind of like the arc length of a really big circle. Why is it an arc length? Well, you got this little sector here that you created with your eyes, right? And so you're really kind of finding out this part here, which is represented by the arc length. Okay, so that's what we're trying to find. We're trying to find the arc length of the circle. And again, this is just going to give you more of an approximation. It's of the diameter of Mars. Okay, so if we think about this as arc length, remember how we can set up a proportion. We can compare the length versus the angle. And the arc length is what we're trying to find. That's the part over the entire circle's full length, right? And the full length is circumference, which is 2 pi r. What is that? Well, again, looking at my drawing here, keep in mind that the radius of your really, really big circle is made up of the 5.6 times 10 to the 7th. So we have 2 pi r, the circumference of our circle, but the r being 5.6 times 10 to the 7th kilometers. Okay, is equal to the angle measurement, the angle formed with your eyes, which we don't know, right? Oh, no, we do know, actually. It was the apparent size was 0.007 degrees. Okay, so what we see with our eyes is 0.007 degrees. So that's the part of the sector we have. So we're going to go ahead and write that in, 0.007 degrees, and compare that with the full circle's angle measurement, which we know is going to be 360 degrees. And then from there, solve for L. Okay, so 0.007 degrees over 360 degrees times 2 pi times 5.6 times 10 to the 7th. Okay, so going ahead to enter that into the calculator. I'm going to go ahead and do that now. Where is it? Here. There we go. Okay, so what do we have here? 0.007 times 2 pi times 5.6 times 10 to the 7th. And then this value is going to then all be divided by 360. There we go. So our answer is going to be a value, the arc length is 6,841.69, and then we are in kilometers here. Okay, so that'll do it for that problem there. Oops. There we go. Okay, so that is the approximate diameter of Mars. There we go.